Alright, in this video we'll be discussing somewhat recent, albeit not as recent anymore, blog post from the company called Unconventional. So there's a bunch of new companies basically that are investigating alternative computing platforms, right, outside of quantum computing or outside of, classical CPU, GPU programming. And one of them is called Unconventional. So we're going to take a look at one of their blogs. At the time that I made this was very recent, but since this recording is being made, there's a bunch of new blogs that we'll probably cover in subsequent videos. But for now, we'll just get into the details of this one. And the basic idea is not very dissimilar from some of the hybrid sort of quantum computing setups that we've covered before. The task, of course, is just any sort of general ML task, right? Like where you have some loss function and you want to train this model, usually through some sort of gradient-based method. And so the example problem here, right, is of classification. So if you have some of your usual if you have some of your usual MNIST digits, then you can, as I'm drawing here, then you can basically classify them into the number that they are, right? If they're a 7 or a 5 or whatever else they might be. The specific setup that they have is actually that of a time series, right? As you can see, as I'm drawing, there's, different actual steps that my pen is taking, and those are basically what are the inputs to this time series model. And so in this model of computation that they have, right, it's not based on qubits and it's not based on normal bits. It's basically a proposal for what they call gyroscope based computing. Really, all this is not really that is actually gyroscope dynamics that's on a chip, but that this is sort of a representation of what alternative platforms might look like, these sort of real physical systems. And so, right, when we're talking about these gyroscopes, it's sort of just like a little mass on a string, on an extensible string, right? So spring dynamics almost. And so if you have one of these, right, you can imagine this, if you have like the position of this could change as the weight gets pulled up or down. It has some equilibrium, right, in an absence of outside forces. If it's just, if there's just gravity pulling it down. And so what is interesting, of course, is not gyrators by themselves, but collections of them. If you took a collection and then you also had connections between them, then information can propagate through the system. Suppose you had a bunch of these. Then you can propagate information through the system. And if you are able to make a physical device which has all of these characteristics, or is actually this physical set of processes, then you can do computation by simply letting the chip do its thing and evolve. And from there, you can basically just measure whatever output variables that you care about. So in this specific case, right, we have a collection of gyroscopes, which basically serve as inputs, and then a collection that serve as outputs. So you have, I'm just going to erase this. If you have a collection of inputs, right, you'll see like these here, they may or may not have connections between them. It's kind of arbitrary. Then basically what you have is a collection of gyrators in between, and then some outputs. And you'll notice, of course, this sort of propagation of information looks very similar to classical networks of various kinds. And if we have some input, this obviously can be any number, it doesn't have to be this specific layer. Then we can see basically if we have some input, some output, and some, in essence, hidden variables, then we can represent the system in a very canonical manner. So that's sort of the outline. We'll get into the code next, which is, as always, shared below in the description, and get into some more details of exactly how this works there. I've also organized in a more sort of formal blog that is linked below if you're interested in reading about it, since as I'm just getting back into making these videos for the first time in a long time, might be a little rusty. Okay, now we're going to be getting into the code. So what we have basically in order to execute this dynamic system is just a standard sort of setup in terms of creating a bunch of gyrators and then integrating them using numerical differential equation solver, and then appending to that the encoder and decoder layers. I realize I'm not really explaining all the details of the blog through this process, so it is recommended that you look at that beforehand. It is kind of painfully AI generated, but nonetheless, if you want some more context, you can see that. But basically, what we're doing here, right, is just creating a system. If you want the sort of bigger picture, broader picture, is creating a system of these sort of physical spring-like gyroscopes, integrating them, and then in this hybrid setup where we have a neural network or a single linear layer, as the case may be, at the end, then we have some task, loss function, and we integrate. I mean, I'm sort of presenting this in a more general way than their blog, right? Because it doesn't really matter if it's time series or what the task is. It's just like you have some physical system that you're integrating, which, and by integrating we just mean letting evolve over time, and then you measure some output. And it's conceptually quite similar to the hybrid quantum computing stuff. So getting into it, right, we're going to use JAX because I like JAX, and then diffrax is a great package for numerical differentiation of ODEs, SDEs. And so the first thing we want to do, you'll notice some differences in some specific setup here, but the first thing we want to do is create basically an instance of a gyrator, and this will be, of course, all the gyrators. We can just operate on the arrays, and there's a number of basically forces at play here. So we have for each gyrator they have the two-dimensional x and y position, and then there's also velocity in the x and y directions, right? And so obviously, like, position and velocity, or position and momentum, is very similar to these Hamiltonian dynamics or Langevin dynamic integrators. You could think about like some symplectic integrator method. I'm just doing a standard sort of Runge-Kutta ODE solver, but that would be an interesting extension of this if you wanted to explore, is basically take this and there's a lot of numerical stability issues that I encountered, but I don't I didn't, really investigate the sources that much. It's possible that, some more advanced integration methods would solve it. But, you know, given this information, basically we have like some starting point, x0, y0, and we basically have some gravitational force, which is basically how far off they are um, from these points in essence. And then we have, right, so you just have gravity pulling things down is all that means. And then we have some force, right, and this force is applied from the input. So like if the input to the gyroscopes is just like something applying a force to some subset of them, and so we have some force that's just being applied, and that force, right, is just like pushing on them in a literal sense. And then there's the damping effects, right, which is sort of obviously in a world with friction, things have damping over time. And then this last interaction is basically for the couplings, right? So all of the previous forces are just acting on one gyrator, but obviously gyrators will interact with each other, and that's something that needs to be modeled. And you'll notice a lot of stop gradient sprinkled through here. This is maybe not the best way of doing it in all honesty, but it is basically just a technique, right? Because we're passing all this around, there's all these arrays. We don't want to differentiate the original starting positions. Those are sort of a static thing. We don't want those to be optimized. And now if you had something like torch, right, you could say like requires grad equal false, but here the way to do that in JAX is just by an explicit stop gradient. Then we have it in a bunch of places. And that's just because like I could just do like x0 equals like stop gradient of self.x0, but I actually remembered to add stop gradients after I wrote it and then ran it, and I was like, oh dang, classic mistake. And so that's just to basically not train, right, these starting positions. And then we have a force. Here the force just applies an array. I don't think that specific force is basically just a lambda function. And then we have a classifier, right? And so what this does is it basically takes an encoder, a bunch of these gyroscopes, and a decoder, and just runs it through. And so one of the important things, right, like in the blog that I kind of do differently here is that you have this force, right, but for each time series input, right, for each stroke of the pin, you apply a new force. And so this is sort of a, not a continuous function, right? There's jumps at these specific points. And so you could interpolate, right? Like you could just do some sort of interpolation between all of these points, or in my case, I chose to just have a sort of piecewise function. And in order to do this, basically, we just have this, we basically just scan over these function outputs, right, or these forces. And so all this is doing, right, is basically saying collect all the forces which are specified from the encoder, right? The encoder takes the neural network, takes the input, passes it through this neural network, or just a single linear layer, and then reduces it down to the appropriate dimension, and then, or expands it to the appropriate dimension, and then we take this these forces and apply them, and we integrate through this physical system. You'll notice some PID controller shenanigans that I was experimenting with. I don't know how much these specific parameters matter. There's a lot of numerical instabilities. Like I think basically the parameters during training, basically. So as you train and the parameters change, then sort of the stiffness of the differential equation can change as well. And then you can have numerical instabilities show up. And so I was just trying to combat that. I don't really know how necessary that is, but you can experiment with it. That's also why you'll see some of these like soft plus operations. That's basically you just have like treating the mass and gamma as like logits to normalize them. Obviously, mass is bounded by to be above zero. Friction, we're just assuming, is bounded above zero as well, and so those help sort of smooth it out rather than just having a clip at like 1e-8 or something like that. And so then obviously you take the output and then you just take some of these like last output layers and then you feed them through the decoder, and you have that. Here we have a grid, which is this sort of triangular lattice grid that you can visualize. We make the classifier with all the setup. We'll download the data. Here again, the data is actually much lower dimensional than is specified in the blog. They say like, oh, it's 100 dimensional, but it's actually 8 when you download it. I don't know why the AI that wrote their blog thought that it was 100 dimensional, but it's possible. My interpretation of that was just that they were doing interpolation. And so I did some linear interpolation of my own. And so you can see what this looks like, right? Like you have this figure and you can see it's an 8, and you can see each of the points represents how you're drawing, right? Each drawing as the stroke goes through. So of course we have a standard classification loss. It's just what is the digit. Accuracy and step functions are all normal. And then we just train it in a very, very standard manner. And then we can run and we see the loss go down, which is always a good sign. And we see the accuracy go up, which is also a good thing for both training and validation. And then what we do next is we plot some of these values, and this is obviously the logit values, so they're not the raw, right? Like the mass is not -5. I don't really know what the importance of interpreting these are. I will let you decide that. It's kind of similar to some of the stuff they did in the blog, right? There's plotting these values. Obviously, like higher mass means you need more force to push it the same distance. So if you have high mass points, they sort of don't move as much. Maybe that means they're not communicating as much information. I don't know. That's just a possible interpretation. And yeah, that's pretty much the summary of it. Of course, the code is linked below. I'm in the process of migrating to a new Git repository that has more than 1.9 of reliability, so that's why there's a new link there. This maybe was, a bit. I don't know. I don't know how helpful all of this was. First video that I've recorded in quite some time. So we'll refine it. We'll refine it as it goes. But that's all I have for this one. There's several more that I have recorded, or am about to record. So, there's some more videos coming in the future. Probably I've said that at the end of like every video. That's then, 1 year later, there's a new video. But it is what it is. Also, yeah, I'm sort of writing some of the results more formally, not really formally, but just like in a written manner. So if you want to see that, you can look at the blog below. Also, I did change the handle of the channel just to be more broad beyond physics originally. So maybe that's a hint as to the broader category of content that hopefully will come.